All right, today I am going to walk you through an example of using the test, the chi-square test for goodness of fit in a special case, something that is important in biology because it is going to be how we can tell if evolution is potentially happening in a population. So if we define evolution as a change in allele frequencies in a population, that's the very smallest amount of genetic change that we could conceivably measure. And if we find that change happening, then evolution might in fact be happening. So if evolution is not happening, then that means nothing is changing, that we're going to have a population whose allele frequencies are in equilibrium. That means they are not changing from one time to the next. And we're going to call this equilibrium in allele frequencies Hardy-Weinberg Equilibrium. All right, so if a population's in Hardy-Weinberg Equilibrium, it means that nothing but random chance is producing gametes and making offspring in the population. So not just the allele frequencies, but the genotype frequencies of the offspring should be the same as the next generation. So we're going to be able to test this hypothesis using the chi-square test for goodness of fit. All right, so if our population's in, Hardy-Weinberg equilibrium, and we have little p allele and little q allele in one of the parents and in the other parents, that is all the parents in the population, so that this little p stands for the frequency of the little p allele and the little p allele itself. We can make offspring that are little p, offspring that are little q, and also offspring that are little q. So p and q are the alleles. And then when we combine two of those alleles together in an offspring, that is the genotype. So the genotypes are going to have two alleles together. And we're going to be able to, if we have the allele frequencies, because we're multiplying together the probability of getting a p allele and a p allele, we're going to multiply together the frequencies. So little p squared is going to tell us the expected frequency of offspring of this genotype. Little q squared will tell us the expected offspring frequency of the QQ genotype. And we're going to take p times q and multiply it times 2 to get the frequency of the heterozygotes. Right, so those are going to be what's predicted, assuming the population is in equilibrium. Nothing is happening here except random chance. So these alleles are acting just like dice, and we can use the mathematics of probability for them. All right, so when we have this expectation of what our offspring should look like if Hardy-Weinberg equilibrium is true, then we can use that as a null hypothesis in our test for Hardy-Weinberg equilibrium. So the null hypothesis is that the population is in equilibrium, that is, nothing's happening. And the alternate hypothesis is going to be that our population is not in Hardy-Weinberg equilibrium. So if we reject the null, then we can accept the alternate, that is that something, possibly evolution, is happening. All right, so we're going to write out our H sub A. We're going to write it out in words, and HWE is going to stand for Hardy-Weinberg equilibrium. It is usually going to be necessary that there's a large sample size or that there's a large population that we're sampling from, because we want to, the population should be acting like any randomizing device. We need to have many randomizations to see the true pattern. And our individuals need to be mating at random with one another. Right? Non-random mating would be where individuals with a certain genotype would choose preferentially to mate with other individuals with the same or a particular genotype, non-random mating is going to change the proportion of different genotypes. All right, so when we look at these values, p squared, 2pq, and q squared, those are the frequencies of the three genotypes. They're always all going to add up to 1. Little p and little q are also always going to add up to 1. Neither of these things proves that Hardy-Weinberg equilibrium is happening. They are just things about frequencies. If we have two things and we add their frequencies together, it'll equal 1. If we have three different things, we add their frequencies together. That will also equal 1. So we're going to use some notation. Let little p be the frequency of, say, the big A allele, and little q be the frequency of, say, a little a allele. Doesn't matter what we call the alleles. And we're going to have a population that we're going to sample. And for each of the genotypes, we're going to take the number of individuals that we observe that are in that particular genotype. And we're going to start with those values. So those are our actual observed values, our number of observed individuals in each genotype. All right. We know those to start with. Okay. Now, all the individuals we sampled, if we take the number in each genotype and we divide by the total number we sampled, capital N, we'll get the genotype frequencies, right? And we're going to call the frequency of the big A combination, big P, the frequency of the big A, little a, or heterozygote, we're going to call that big H. And for little a, we're going to call that genotype frequency big Q. All right, once we have found capital P, capital H, and capital Q, we can find the allele frequencies from our population. Right, so we started out knowing the genotype. Each individual has 2 alleles. We need to know how many we have of each genotype in order to figure out the allele frequencies. Right. Once we find capital P, capital H, and capital Q, we can find little p, the allele frequency of the big A allele, by taking capital P plus 1/2 H. And then similarly, we're going to find the frequency of the little a allele. We're going to call it Q, and we're going to take capital Q plus 1/2 capital H, right? And little p plus little q should equal 1. All right, so we had a count of individuals of each genotype. We converted that into a genotype frequency. And then from the genotype frequencies of the observed individuals, we're going to find the allele frequencies. All right, we're going to use the allele frequencies to calculate the expected genotype frequencies that they should have in their offspring. All right, the expected genotype frequencies they should have in their offspring is going to be based on what would happen just if nothing but random chance were happening. So we're going to take p squared, 2pq, and q squared, right? And that is going to give us expected genotype frequencies. And if we multiply it times capital N, that's going to convert it from a frequency into a count. So these will actually be our expected count of each genotype that is going to be equivalent to the count of the genotypes that we started out with. All right, so when if we're gonna do a test to see if we're in Hardy-Weinberg equilibrium, we're gonna start with our null hypothesis. The population is in Hardy-Weinberg equilibrium. Our alternate hypothesis, the population is not in Hardy-Weinberg equilibrium. And we're going to work through an example so you can see how this works. So we have 2 alleles here. We're going to call them big M and big N. And we know the frequency when we find the allele frequencies for each of these two alleles, we're going to find the expected offspring. Now, it turns out if a population's in Hardy-Weinberg equilibrium, then the genotype frequencies of the parents and the expected offspring should be the same. So if they are not, then our population is out of Hardy-Weinberg equilibrium. All right. So we are going to find the frequency of the big M allele, and then we're going to find the probability of offspring of the three different genotypes. And then we're going to convert that to a count. And then we're going to compare the observed count of individuals to the expected count of individuals using our chi-squared test. So here's an example. We've got the big M genotype. We have 1,787 individuals. We have the big M, big N genotype. We have 3,039 individuals. And then for the big N genotype, we have 1,303. And these are a type of blood type, right? So we need to add up all of our individuals to get our capital N sample size, 6,129. And we're going to use the total sample size to find our genotype frequencies. Our genotype frequencies we're going to call big P, big H, and big Q. So we're just going to take each of those counts and divide by the same value, 6,129. So out of our three genotypes, we're going to get 0.292 as the genotype frequency of the big M genotype, 0.496 as the genotype frequency of the big M N genotype, and 0.212 as the genotype frequency of the big N genotype. All right, so we're going to come back to these counts, right, because we have to put those into our chi-square test as our observed, right? We need to find the expected, and we're in the process of doing that. All right, so we need to find the allele frequencies for the two different alleles. We've already found our capital P, our capital H, and our capital Q, so we can do that. So we're going to take 0.292 plus 1/2 times 0.496, and we get 0.539 as our frequency of the little p allele. We're going to do the same thing for the other allele. This part of the equation is going to be the same for both, but the little p, sorry, the big P versus the big Q is different. All right, so we get 0.461. Now these two values should add up to 1, and they do. All right, so we have a pretty even distribution between these two alleles in our population. All right, now we found the allele frequencies. We need to use those to find the expected values for our chi-square test. And assuming our populations in Hardy-Weinberg equilibrium, we can find the expected count of individuals of our big M genotype by taking capital N times P squared, right? So we're going to go through these steps using capital N times 2PQ and capital N times Q squared to give us our expected counts. Now this part, the P squared, the 2PQ, and the Q squared give us the genotype frequencies, but we want to compare them to counts. And so we use our sample size to convert those from frequencies to counts. All right, so here we've done the math. We've got 6129 times 0.539 squared. That gives us 1783.8. Right now, we don't usually have decimals for counts for our observed. In fact, we shouldn't. but we can have decimals for our expected values. They don't have to round off exactly to a whole number because they're calculated from those frequencies. So we're going to have our expected values of 1,783.8, 3,045.4, and 1,299.8. So we found our expected values that we need to do our chi-square test. And we want to write those down into a nice little table so it's easy to see. If we went back a few slides, you'd see that these are the values we had at the very beginning, and these are the values that we calculated using the allele frequencies. We're going to use our same chi-squared equation, the sum of all the observed minus expected squared over expected. We have 3 pairs of observed and expected values. And so our sum is going to have 3 terms in it. We're going to take 1787 minus 1783.8. We're going to square that and divide it by the expected. Same thing for each of these 3 pairs of values. Always dividing by the expected. And our last one, 1303 minus 1299.8. We're going to square that and then divide by the expected, 1299. All right, so we're going to do all these calculations, add those 3 terms up, and we're going to get chi-squared equals 0.027. All right, so we've calculated, we had our null and alternate hypothesis, we calculated our test statistic. Now we need to find the degrees of freedom and use our chi-square distribution table to find out the p-value. All right, so even though this is a decimal number, remember we're calculating a chi-squared value here that's equivalent to a little t or a little z, and we need to use our distribution table to find the probability of getting this value of chi-squared. All right, for Hardy-Weinberg equilibrium problems, degrees of freedom is going to be number of genotypes minus number of alleles. And so we are just going to do 3 minus 2 equals 1. And so our degrees of freedom for all these Hardy-Weinberg equilibrium problems, it's always going to be 1. Until we go on to a higher level class and we have more than 1 gene, we have more than 2 alleles. But for this class, we're always going to do 2 alleles, 3 genotypes, and we're going to get degrees of freedom of 1. All right, so go to your chi-squared distribution table. And what we're going to find is that our chi-squared value is going to be off the table, right? It's going to be off the table to the left. And so all we can say is that our chi-squared value is going to be, our chi-squared value is less than 1.32. That's the smallest one on the very left-hand side of the first row of our chi-squared table. And when we go down to the bottom and we look and see what the probability is, that means the probability is greater than 0.25. We have to say it's greater than this because again, it's fallen off the edge of the table. All right, now if we use an alpha of 0.05 or we use an alpha of 0.01, it doesn't matter that much because our p-value is pretty large, right? Our p-value is not small. Is our p-value less than our alpha? No, it is not. Therefore, we do not reject the null hypothesis. And we would say for this population that we accept the null. So the population is in Hardy-Weinberg equilibrium. Oops. Here we go. Okay, do not reject the null. The population is in Hardy-Weinberg equilibrium. All right, that is the structure and pattern you're going to use to calculate and do calculate expected values and do a chi-square test for goodness of fit in the special case of testing for Hardy-Weinberg equilibrium.